Okay, great. So let's continue on last week discussion. Sorry. So this week, actually, the discussion we began on Monday. So on Monday, we began discussing how to introduce local symmetry, going from a global symmetry to a local symmetry. And we basically use the U1 example. So the U1 transformation, the U1 symmetry, just to give you an idea of the basic procedure, which is when you promote this to a global symmetry or local symmetry, you introduce covariant derivatives. We introduce covariant derivatives here. And once we have the covariant derivatives, the definition of covariant derivative is such that it contains a derivative term and a correction term. And you define that under the transformation, the covariant derivative, under the transformation, the covariant, where did I write? Oh, here. The covariant derivative should transform in this matter under your local transformation. And from this, we can deduce that the correction term or the gauge field or the connection should transform in this matter. So we automatically derive the form in which your gauge field should transform. So said in another way, the whole point of having a gauge field is to modify your derivative in such a way that under local symmetry, the derivative itself, the covariant derivative, transformed in the same ways as the ordinary derivative. So today what we're going to do is we're going to start generalizing from, so last week we were doing this this U1 symmetry, which is the simplest symmetry, that the simplest continuous symmetry that we can have. And so today we're going to generalize to more general symmetry, and then go into the symmetry that is more relevant to gravity. So in general, so today we're going to talk about general local symmetry. So what do I mean by general local symmetry? What I mean is that as you remember that when we're talking about local symmetry, we mean that we have some symmetry transformation G, where this G has some parameter, let me call it alpha, right? Where alpha can be continuous. So now let's say if alpha contains an index, which means that you can have more than one alpha, then since this is a symmetry transformation and that this is a continuous parameter, that means that when the parameter is small, when I have alpha I goes to very small, that means that we can have that when alpha I is in the small limit, this must be the identity plus some factor, I mean, right, alpha A times GA. Okay, and then of course we're going to add higher order in alpha, so alpha square terms. So this just means that it's square. Okay. So this I is just convention. Sometimes in some, so actually in most sometimes in the GR literature, you might not have this I here. So I is just a convention. If you don't have this I, you can define things without an I, and then that just means that your GI will might have an extra factor of I relative to other conventions. Okay, but let's just do an I here. Okay, so these GAs are what we call the generator of the symmetry transformation. Okay, now in our previous case, when we have U1 transformation, we know that in the U1 example, when we had the U1 example, we know that our G looked like exponential I alpha, right? So that means that in the alpha goes to 0 limit, my G looks like 1 plus I alpha. So in that sense, my generator G, so that means that my generator G is just equal to 1, or it's just like some constant. Okay, it's just some number. Okay. So of course, in general, you can have G to be different. So just use something that is more familiar to you guys. So for example, I can consider, for example, an SO3, sorry, a rotation transformation, which is something that you guys are familiar with. If I consider a rotation along the z-axis, then you know that G is given by cosine, sorry, let me just call this. So G alpha is given by cosine alpha, sine alpha, minus sine alpha, cosine alpha. And let's say we have 0, 0, 1, 0, 0, right? So our transformation is a matrix. And that means that in the alpha near 0 limit, I have something that looks like 1 plus alpha times 0 alpha, sorry, 0, 1, minus 1, 0, 0, 0, 0, 0, 0. Okay, plus order alpha squared. So now you see, well, actually, first thing, now this 1 is no longer just a number. This 1 here is no longer just a 1. It's actually identity, an identity 3 by 3 matrix. Okay, so here now our G, our generator of this rotation along the z-axis, our G now looks like 0, 1, minus 1, 0, 0, 0, 0. And you can see what happened, what happened, right? So you take alpha goes to 0 limit, this sine alpha is given, becomes alpha. And that's why at the linear order in alpha, this is 1 and this is minus 1. This is minus sine alpha. Okay. Can someone tell me what happened to the cosine alpha? What happened to cosine alpha and the alpha goes to 0 limit? What?
About 1.
It's about 1, right? And where did that 1 go? The 1 is here.
Identity matrix.
Exactly, it's identity here, right? Very good. Okay, good. So this tells us, so here we define the generator. So once we have the, oh, sorry, if I should follow this kind of notation, then my generator is actually G, because I have my generator, my generator normalized by I here. So here I should put a minus I here. I should multiply by a minus I because this is real. Okay, good. So in this case, so generically, we're going to have generators of our transformation, and so generically, so this is in the alpha goes. This is in the alpha goes is a small alpha limit. So at finite transformation, usually we write finite transformations. So usually we write our G alpha A as an exponential I alpha A GA. Okay, where now the repeated indices I sum over. So the repeated indices, sorry. So the repeated indices here are summed over. So this is summed over. Okay, of course, obviously, if I just take alpha goes to 0 limit, I reproduce the definition here. Okay. Once again, so if G is a matrix, then this is a matrix formula, and you can define this as basically just the identity plus I alpha A GA and plus the higher order terms, if this was a matrix. Okay. Now, as been mentioned in the apply math class, which we're actually talking about these kind of transformation now. So actually, this is a very nice time when if you're taking both classes. We know that actually, if this generator is actually generating some kind of group transformation, then we know that the generators G must satisfy an algebra. So we know that GA and GB must satisfy the commutation relation, must satisfy an algebra that looks like this. And let me write this. Okay, said in another way, the commutator of GA and GB must give something that is that the commutator of GA-GB can be re-expanded on the basis of generators, where the basis or the expansion coefficient, the FABC, these are called the structure constant. Okay, and so basically this is saying that GA-GB, you compute the commutator, whatever the result of your commutator is, it must be re-expandable. You can re-expand it as linear combinations of the generators themselves. Okay, so, and the reason that you need this is very simple. It's because that, let me just erase these things here. So actually now I'm going to try to write in the same page as much as possible, so that we don't go back and forth between pages. So the reason is very simple. It's because that we're saying that G is written as exponential I alpha A. Sorry if I do it with the upper index. Alpha A GA. Now, if G is really a transformation, it better be that if I do a transformation with the parameter, let's say alpha 1, and then I do another transformation with the parameter alpha 2, sorry, with the parameter alpha 2, it better be that the result of successive transformation results in another transformation, where this transformation is just with some other parameter alpha 3. Okay, so it's just like if G is about rotations, then two rotations, the result of two rotations, irrespective of which axis you're doing your rotation with, the result of two rotations should just give you another rotation. So that's basically what this formula means. But if you write these transformation G in terms of the generators, then this is a very non-trivial constraint on your generators, because we know that if we plug this representation into this requirement, then I have exponential I alpha 1 A GA times exponential I alpha 2 GB. But you know that exponential x times exponential y is given by exponential x plus y plus 1/2 xy commutator. I guess this we've already learned in for those of you who've taken Apply Math 1, you've already seen this before with higher order terms, and where the higher order terms are always in terms of these commutators. Okay. So that means that here, this is going to give you equal to exponential I alpha 1 A GA plus alpha B GB. That's very nice. But then you're going to have terms, sorry, this is alpha 2. Then you're going to have term that looks like alpha 1 A, alpha 2 B, and then the commutator of GA GB with a half. And of course, you're going to have higher order terms. Now remember, what is the requirement? The requirement is that the two transformation, the result of two transformation should still be the same type of transformation. So that means it should be still written as G. But you know that G is written as exponential with linear combinations of your generator. So that means that all of these things on top of your exponent has to be linear in G. has to be linear in your generator. Okay. Now, if we look at it closely, this is linear in generator. Great. This is linear in generator. The non-trivial thing is that this is not linear in generator. So the requirement that indeed this forms what we call a group or two successor transformation is equivalent to another transformation. We must have that the commutator be the result of your commutator be linear in your generator. So that's why we have this formula. We have that the commutator of two generators has to be linear, can be linearly represented by my generator. And the linear expansion coefficient is what we call the structure constant. Okay. Good. So the G's should satisfy these transformation. Of course, by definition, from the definition of your structure constant, you already immediately see that FABC is antisymmetric in AB exchange, right? Because these are antisymmetric. Okay. So FABC will be a very important object. And in fact, as you've learned in your applied math class, that the FABC actually defines the group. You can use FABC to define the entire group. Okay, the entire group structure is encoded in FABC. And in particular, the FABC must satisfy non-trivial, the FABC must satisfy non-trivial identity because of the fact that we have the Bianchi identity, which is the following commutator is 0. So if you write this out, then this commutator is 0. So this is an identity. It doesn't matter what ABC is, as long as this is just a definition of your commutator. So so in other words, if something is defined through a commutator, that thing better satisfy this identity, because this identity is just a consequence of commutators. So if you just expand this out, for example, this term just gives you A, BC minus CB minus BC minus CB times A, right? And so you basically expand all of these terms out, and then you'll see that they all come in pair. They will all cancel pairwise. Okay. So this is an identity of your commutator. So if something is defined through a commutator, then it has to satisfy this identity. So our structure constant is defined through the commutator of our generators. Therefore, our structure constant must reflect this identity. And indeed, you can show that the structure constant satisfies. So the way to do it is, let's say A is GA, B is GB, and C is GC. Then you have that. So for example, the first term. Let me just work out the first term, and the other two terms will just be permutation of my ABC indices. So as long as I work out the first term, the other two terms we can just derive directly. So the first term, let me just substitute these things in for ABC. So the first term is just GA with GB GC commutator. Now, as we already know, that GB GC is equal to just using the formula before, we know that GB GC is expandable on the basis of generators. Therefore, this is IFBCD with GA GD. But then once again, this defines another commutator, and therefore this gives you minus FBCD FAD EGE, right? So this is the result of applying the commutator, and then I can just plug this result into these things with just ABC permuted. So I get the identity that minus F B C D F A D E minus F A B, sorry, let me see, A, so A becomes, okay, maybe let me just do this carefully. So A becomes B, so let's write this out. So minus F, so of course this is the same. So A becomes B, so this is B, and A becomes B, B becomes C, so this is C, and CA, right? And doing the similar thing here, you're gonna have F, A, B, D, F, C, D, E. So then you just have this identity, which has to be 0. Okay. So this is usually called either the Jacobi or the Bianchi identity, depending on how you're using it. Okay, so here we'll just call it the Jacobi identity. So once again, you derive this identity as a consequence of the fact that these FABCs are defined, these FABCs, the structure constants are defined from the definition of commutators. Okay. Any questions? Okay, good. So, for example, you can show that if I let FABC, so let's say if FABC is equal to, for example, epsilon AB D delta DC, for example, if I write it like this, so this is the 3-component Levi-Civita symbol, the 3-component Levi-Civita symbol, then you can show that indeed this satisfies this property here. Okay, and the reason I know this satisfy this property is because this Levi-Civita symbol is the symmetry group of SO3. It's a structure constant for SO3. Okay. Okay, perfect. Now, so now we've understand how. So what have we done so far? So what we've done is that we say that for a general continuous transformation, we can write our transformation in terms of exponential I alpha G. But this is the and previously we have G equals to 1. That became our U1 transformation. But in general, G can be any basis of transformation, such that the basis of transformation must be that the commutator of G is linearly expandable on the basis itself. So once you have this, this allows you to define the structure constant. Okay, good. So what are we doing this? Well, remember, so now we can again do the same thing and then make this local. Let's talk about local transformation, the local version. The local version is just that G is equal to exponential I alpha A, but now alpha is X dependent. Okay. So now we should have an SOP, right? We have SOP whenever we have something that goes into a local transformation, we should directly have directly a set of things that we should do. So for example, we should write down our covariant derivative, right? The covariant derivative should have the identity, sorry, what am I doing? So the covariant derivative has the original derivative part plus some gauge field part. Okay, we'll talk more about how this gauge field reflects the fact that now you have a non-trivial generator. But remember, how do we define the covariant derivative transform? We define that under the gauge under this local transformation, the covariant derivative must transform as equals to transform into delta mu prime, where delta mu prime is just G delta mu G inverse. Okay. So let's assume that GA is Hermitian. So let's assume that our transformation or our symmetry group has that our generators are Hermitian matrices. Okay. So that means that you immediately see that that means that the covariant derivative G minus 1. So now I can just plug this into here. So I have that this is exponential I alpha A, sorry. Exponential I alpha A GA delta mu times exponential minus I alpha A GA. Okay, the reason that the inverse is just a minus here is because my GA is as Hermitian matrix. Okay, great. So the standard procedure is to define a covariant derivative where the covariant derivative transform in this way. Once we know that the covariant derivative transform in this way, this tells us what the correction term inside the covariant derivative transform is. Because as we mentioned, we can now expand this into partial mu plus I A mu prime, right? So that means this is telling you how A transform into A prime. On the right-hand side, this becomes equal to exponential I alpha A GA partial mu plus I A mu times exponential minus I alpha. Let me use B, another index instead. Sorry, this is B. Okay. Okay, so let's work out how this transformation works. So this, let me just cut this. Okay, first of all, let me just erase this here. We don't need to use this later on. Okay. So, yeah, sorry. So I should place this here. Okay, so we have this. So let's just write this out. So of course, on the right-hand side, let me use a nicer color. Which color I have not used? I haven't used pink before. Let me use pink. So all right. So here this is exponential I alpha A GA partial mu exponential minus I alpha B GB. So plus exponential I alpha A GA I A mu exponential minus I alpha B GB. So first, this equation, so this part should be trivial. This should just, because the only thing that has x dependent is here, right? This is the only thing that has x dependent. So that means that this term is just equal to partial mu times, so this, let me just put minus I here, minus I partial mu acting on the alpha B of x times GB. Okay, this is what this term looks like. Okay, is there any questions? Everybody okay with this? Okay, now this part. Now we know that this is, so now you see that there's something, there's something interesting. So here you have partial mu acting on alpha B. Oh, sorry, of course, then there's also the term where alpha mu, this derivative doesn't act on anything. So I forgot that trivial term. So we should have this term here. Now, of course, the left-hand side has to equal to the right-hand side, and therefore we know that this term is just going to cancel out this term. So let me just erase it. Let me just erase it, and then I can erase this term. Now, remember, we're equating the left-hand side with the right-hand side. The right-hand side has an expansion. I mean, there's of course extra terms that come from here, but forget about that at the moment. But here you already see that this has an expansion in terms of the generator. Okay, so in order for this equality to even make sense, remember, whenever we write an equality, it can be both stupid and also it's very important. So it's stupidly important or importantly stupid. The stupid is, of course, the two things on the two sides are basically the same thing. So in a sense, that's stupid. But it's important in the sense that they must be of the same nature. So if something is written in terms of linear combination of your generator, that immediately tells you that the correction term here, I should actually write as follows. It should also be a linear expansion in terms of your generator. So this should actually have another GA. I should also expand that on GA. Otherwise, this equality makes no sense at all. So this is one of the very important things, okay? When we're making a symmetry group into a local symmetry, the number of correction terms that you need to introduce is the same number of generators that you have, right? Because for each generator, you're going to have a correction term. Or for each generator, you're going to have a gauge field, right? Or a connection. So the number of generators in your transformation equals the number of gauge fields when you make the symmetry into a local symmetry. So in the previous case, when we have U1, you only have one generator, right? Because it's just one. So in U1, you just have one generator. And therefore, the number of gauge fields or the number of connections that you needed to introduce was only one. You only needed to introduce a mu. So our photon fields, which is, or electromagnetic field, which is a gauge field, is a gauge field of the local symmetry U1. And since the generator of U1 is just one, you just have one photon. Okay, in our world, we just have one photon, so we only need like one pair of eyes. Right? We don't need two pairs of eyes, one to look at one particular photon and the other to look at another kind of photon. If our symmetry group was greater than just U1, then the number of gauge fields is going to be more. So for example, for many of you, you've heard who've studied particle physics or learn a little bit about it, you know that the nuclear force are mediated by a gauge group of SU3. In SU3, the number of generator is 8. There's eight different generators in SU3. And therefore, that means that in the nuclear force, which we call QCD, you actually have 8 different gauge fields. You have 8 different gluons. Okay. So this is the first important point, is that just by this transformation alone, you know that the correction terms here, the correction or the gauge field terms, have to match with the number of generators. It must be expandable on the generator. Okay. So that means that here, here the dot here, I should really also write it as let me use. So I should also write this as exponential I alpha A GA times I A mu. Let me call it CGC. I should really write this as an expansion on the generator. Okay. Of course, on the left-hand side here, I'm only expanding things up to linear order in alpha. So I should really write, so this is not entirely correct. I should really write this. So let me just erase this, erase the equality. The correct thing I want to write is actually, so here I have minus I partial mu alpha B x GB. Here I need to expand. So I want to expand up to linear order plus I alpha, sorry. So this is actually minus. So minus alpha A GA GC times A mu C plus, so this term comes down, becomes plus alpha B GC times GB. Okay. Now, of course, these are just stupid dummy variables. So I can, whether I call it A or B, it doesn't matter. Okay, so these are just stupid dummy variables here. I mean, they're supposed to be sum over. So whether I call it A or B, it's the same thing. And so let me just call it A then. So let me erase this little guy here, and let me just call this, let me just call them A. So the reason I want to write it like this is because you already know, right? Because this I can recollect things. So this term here, I can recollect it and write it as partial alpha A mu C, and the commutator of GA, GC. Right, maybe, sorry, I should probably put a minus sign here. Okay. But you know that what is GAGC? GAGC is just I alpha AC, let me see, AC, let me call it BGB, right? The commutator of the two generator is once again expandable on the generator itself with this extra linear proportionality coefficient. So now we're ready to put everything together. So after I write it in this form, so let me just erase this. So let me just erase this here. Give me a little bit space. So now I have that this is just equal to minus I. So since I know that here this is A, I'm going to call everything A. Sorry. So partial mu alpha AX GA. Okay, I'm just changing B to A. Minus I alpha A F A C B. Oh, sorry, this is probably not good. I'm going to exchange A and B. So instead, because I want to make all my G's called A. Okay, so then this is F A C. Let me call this B, and then this is alpha B, and then this is A C mu. Okay. Great. So now we see that the right-hand side is equal to this, right? So we can finally write down how A mu primes transform. Since now we can remove the GA because everything is in terms of GA. So now they're the same thing. So now I get that my gauge field A mu prime A should transform as minus partial mu alpha A minus alpha B A C mu F B C A. Okay, so this is how our gauge field should transform. Okay, so once again, if we go back to our previous U1 example, then because we just have one generator for our, so our FABC is 0, so we just go back to our original form, which is just a single derivative. Because of the fact that our commutator is not 0, so in other words, because of the fact that our GAGB is not 0, that tells you, or the fact that there's a non-zero structure constant, that gives us an additional term. Okay, so this gives us an additional term here. Okay, this is a reflection. So a reflection of the non-abelian nature the non-abelian nature of my symmetry. Okay, the non-abelian nature of, by non-abelian just means that my symmetry group GA-GB commutator is not 0. Okay, that's what we mean by non-abelian. Okay, is there any questions? Okay, fantastic. So sometimes people would instead prefer to write things in this way. So instead of writing how A mu prime A transform, they still prefer to just write A mu, where A mu is just defined as A mu A times GA. So they prefer to write this as A mu prime is equal to, so in this case, then it'll be equal to partial mu alpha minus the commutator of alpha and A mu. Okay, so now you see that alpha is also contracted with the generator. Okay, great. Okay, so from this, so we immediately see that we can now, so we've established two things, right? So we have established that our covariant derivative now, so we've established that our covariant derivative delta mu is now written as partial mu plus I A mu, but importantly, my A mu A should transform should be carry an extra index A, which contracts with the generator of the group, which I'm going to try to make it into a local symmetry, and therefore furthermore my A mu transformation is going to, my A mu prime is going to be equal to A mu so sometimes, sorry, I should really write this as, sorry, I should really write this as the variation of it, because this is small. Sorry, guys. I should really write this as the variation in this sense, because I'm really expanding my. Oh, okay. Sorry. Let me take that back. So let me be a little bit more careful. So this was A mu prime. But starting at this order, it becomes yes, sorry. So there's supposed to be an A mu here, right? Because obviously there's an A mu here coming from, or A mu C GC. Sorry, the mu should be in downstairs. Sorry. So there's obviously this term here. And of course, then I should take this to the left-hand side and make I A mu prime minus. So then if I take this to the left-hand side, I get I A mu prime minus A mu. It's C times GC. And therefore, this is variation of A mu. Okay, so really here, this is not A mu prime, but really the variation of A mu. Okay, sorry. I mean, it's just something trivial, right? So you do the transformation. Just the transformation on the right-hand side, of course, will include a term in the expansion of this that involves just the A itself, right? Because you're expanding both sides. So there's the identity from the exponential and also the identity from here. So there's obviously going to give you the A mu part. And once you take the A mu, you just take it to the left-hand side and you do the subtraction here. And then we call the difference. That's the transformation, the difference between before and after the variation of A mu equals to this. Okay, sorry about that. So that means that I have that my variation of A mu is equal to be minus partial mu alpha A minus alpha A G, sorry, alpha A B mu F, sorry, this is supposed to be BC. Okay, so good. So now we've established these two terms. Okay, now once again, we write down our Lagrangian. So we go back to our Lagrangian. Then originally, once again, if we originally have phi and partial mu phi, now we convert this into phi, and instead covariant derivative acting on phi. Okay, and since it's covariant, but if it's covariant derivative acting on phi, then we can also have what is called, what we introduced last time, which was the field strength. So let's see what the field strength is now. So the field strength, if you remember, is just equal to the commutator of my covariant derivative. So I can expand out and write my covariant derivative. So my covariant derivative is here. So it's just partial mu plus I A mu A GA, and then partial nu plus I A nu, let me call this B GB. Okay, and once again, expand this out. I immediately have I partial mu A nu A GA with this anti-symmetrized. Once again, if I have partial, if I have something that is, so if I have nu anti-symmetrized, that just means that I have partial mu lambda nu minus lambda nu, partial nu lambda mu. Sorry, this is probably not good. Okay, that's what this symbol means. So this bracket means that it is anti-symmetric. Okay, good. So we have this term here, but now notice, so this term corresponds to this derivative. This term corresponds to this derivative acting on this guy, and this derivative acting on this guy. But of course, we can have, now we have something new. We have terms where there's no derivative at all. So that means there's a minus term here, and then we're going to have A mu. Well, actually, I can pull the A mu out because A mu is just a function. So the really non-trivial thing is just a GA, GB, and then I have A mu A, and then A mu B. Okay. And now, again, I use the same thing. My GA-GB is going to be IFABC, GC, right? So I can write this as, so this will be, and this will be the final. So I end up with I partial anti-symmetrized A nu A GA minus IFABC A mu A nu B GC. Okay, so I can collect everything together. So I can now write this as equal to I times, let me just do a bracket so I can pull everything outside. Let me call this GC outside. So this will be partial anti-symmetric A nu C minus FAB C A mu A nu B. Okay, so this will be, so once again, my field strength. So this is, so usually we call this a field strength. Okay, this we call a field strength. So now our field strength, because of the non-abelian nature of my symmetry group, therefore now my field strength is also expanded on my generators. Okay, and unlike the abelian case where FABC is 0, now you see that my field strength now contains terms that are quadratic in my connection or quadratic in my gauge field. Okay, good. Now, once again, as we've discussed previously, the field strength, since is defined as the commutator of your covariant derivative, therefore the field strength transform as how the covariant derivative transforms, right? So the transform as how the covariant derivative transforms. But we already know the covariant derivative, the transform covariantly, right? So we know that this actually transform as G delta mu G minus 1. Sorry, so this is G delta nu G minus 1, right? And of course, this, because the G minus 1 is going to cancel the G, so this just becomes G commutator delta mu G minus 1. Okay, so that means that the transform field strength is equal to G times F mu nu times G inverse. Okay, so this is generically, so the field strength, so here you see that generically, the field strength transform covariantly. It's not invariant, it's covariant. Under G. It's covariant, not invariant. Okay. The reason that in the U1 case it was invariant was because the G is just the phase. So you just have the inverse phase and G, and now you can just commute the G over here and then they can cancel because there's just an overall phase. But as you see now, my field strength itself is already expanded on a matrix. So my field strength is actually a matrix. And my G and G inverse is also matrixy. So you cannot just jump ahead and make G over here and cancel it. And so that's why this is no longer invariant, but a covariant. Okay. But we can still writing, so you might ask, okay, so now I have some field strength that is covariant, not invariant. So why do I care about field strength now? Wasn't the whole point being starting from a Lagrangian, I want to write things which I can make it to be invariant under my local transformation? Well, the fact that you have covariant objects is also important, because if you have covariant objects, then you can still make invariant quantities out of your covariant object very easily. So for example, since now we know that our field strengths transform covariantly, that means that we can write something like this. So let me write trace, sorry, bad color. So we write trace of F mu nu. So the claim is that this is invariant under the previous transformation. Okay, so this is an invariant. Why? Because of course, under the transformation, the trace of F mu nu becomes something that so become trace of G F mu nu G inverse G F mu nu G inverse. Okay, this is how it transforms under the local gauge transformation. Once you see that it transforms like this, you immediately see that this cancel. So you get equal to trace G F mu nu and then F mu nu G inverse. Now this is still not invariant. Can someone tell me why this is invariant? How does the G and the G minus cancel each other?
The cyclic invariance of trace.
Good, because we're sitting inside a trace. Therefore, we can take the cyclic transfer, so we can rotate this, and this is equal to trace G minus 1 G F mu nu F mu nu. Or maybe this should be downstairs. Right, this is F mu nu, and therefore this is indeed invariant. Okay, so we see that trace F mu nu now becomes invariant. Great. So that means in general, so that means the general gauge invariant Lagrangian will take the form, so your Lagrangian is now going to be equal. So of course now, for example, if you have scalar fields, then you're going to have covariant derivative phi acting on covariant derivative phi bar. So you have to do the phi bar here. Okay, and then of course the phi and phi bar can still have some, so we can still have some random potential of phi bar. And then we're going to have minus 1/4 trace of f mu nu, f mu nu. Okay, of course you can have, let me call it higher, let me call it irrelevant, which means that these are additional terms. So you can add, where you can have arbitrary polynomials of f mu nu, you can have arbitrary polynomial of f mu mu, covariant derivative acting on phi, and of course you can have covariant derivative acting on f mu mu, and you have a bunch of things that you can further add to your Lagrangian. But usually we only focus on this part of the Lagrangian, because for those of you who've learned a little bit quantum field theory, this is the renormalizable part. Okay. Now this piece here, this important piece is known as the Yang-Mills Lagrangian. It has a very interesting story. Interesting in the sense that that of course Yang is C and Yang. The interesting story is that actually this action was not first derived by Yang-Mills. Okay, it was actually first derived. You can have that the people realize that this was actually already understood in gravity, which is actually kind of opposite the way that we're telling the story now. So the way we're telling the story now is we're just talking about local gauge transformation. We start with Maxwell equation, leading to this Yang-Mills Lagrangian, and later we're going to go into gravity. But in the original the description or how the history actually happened was that we first had gravity, Einstein equation. Then I guess some of you heard of this before. People tried to unify gravity with electrodynamic, and so this was what was accomplished famously by Kaluza and Klein, which is they consider gravity in higher dimensions. So they consider, for example, in 6th dimension or higher. So they started with gravity in higher dimension. They just started with the Einstein-Hilbert term and then just look at the higher dimension Einstein-Hilbert term. But they imagine, so really, I mean, these people are really imagining. So this is like really in the beginning of the 19 teens. So more than 100 years ago, people have been thinking about higher dimensions. So they thought that if you imagine that the gravity is in 6 dimensions, and then you imagine that 6th dimension is separate, is actually given by a 4-dimension space which look like ours, and an extra dimension space which is really small, so we can't really see. So then they reduce the Lagrangian to see what we actually see in 4 dimensions. And what we see in 4 dimensions is, of course, 4-dimension gravity. But then there's these extra fields, and these extra fields is exactly formed. You have extra vector fields, and these extra vector fields indeed just gives you exactly the Yang-Mills Lagrangian that you have here. And of course, one of them can just become the Maxwell equation. So that was one of the early days when people try to unify Maxwell equation with gravity, and that's to go into higher dimension. Of course, people didn't really pay much attention to these work because of the fact that when you reduce the higher dimension gravity to 4 dimension, you can always do that. So I mean, you guys can now do that, right? So then let's see if someone can answer this question. You guys know that in 4 dimension, the gravity has 2 degrees of freedom, right? We did this degree of counting. So how many degrees of freedom in 6th dimension does gravity have? So in 4D, gravity has 2 degrees of freedom. So how many degrees of freedom are there in 6D? Does anybody know? Remember, we did the counting before, right?
9 degrees of freedom.
Very good, very good, excellent. You have 9 degrees of freedom in 6 dimensions, right? So remember that in any dimension, the way of counting, actually, I'm not even sure if it's 9 degrees. That was fast. But let's do the counting again. So in 60, so remember, in the end, you can always fix using gauge fixing to fix the gravity to just remaining to fix the first and the last column to be 0, and the first and the last row to be 0, and the first column and the last column to be 0. So then that means that this matrix is a D minus 2 times D minus 2 matrix, right? But it's a symmetric matrix, so that means that it's D minus 2 times D minus 1 divided by 2. And of course, we need it to be traceless to get minus 1, right? So if D equals 6, then this is 5 times 4 divided by 2 is 10, and indeed you have 9 degrees of freedom. So if you start with D equals 6 and then you compact the phi down into 4 dimension, you'll see that you're going to get 2 degrees of freedom associated with gravity. For massless fields, so a massless spin 2, you have 2 degrees of freedom. For massless spin 1, you also have 2 degrees of freedom. So actually here you have 3 spin 1, which is of course 2 degrees of freedom. And this 3 spin 1 can be what is known as SU2, the SU2 Yang-Mills theory. Okay. So you have, the reason you have 3 spin 1 is precisely because you have 3 generators in SU2. You'll notice that if you have 3 spin 1, each has 2 degrees of freedom. And if you have a spin 2, you have 2 degrees of freedom. And you add them together, you have 8 degrees of freedom. But we say that you have 9 degrees of freedom. So which degrees of freedom? So there's one thing missing. What can it be? What has a, since we're talking about gravity, so it's always massless. So what is massless but only have 1 degree of freedom? So spin 2 has 2 degrees of freedom. Spin 1 has 2 degrees of freedom. So what is massless but have no degrees of freedom? Anybody?
0.
Good, very good. 0, spin 0. So the scalar case will have 0 degree of freedom. Okay, so it is precisely because of this fact that this higher dimension reduction always gives you 0 degree, have it the spin 0 degree of freedom is why people didn't pay attention to this much in those days. Because remember, whenever you have massless degree of freedom, we're supposed to see it, right? In principle, because these are long-range forces. Anything that is massless degrees of freedom will generate long-range forces. So the very fact that we don't see these things at long range means that this doesn't fit our description of nature. Okay. But anyway, so this is the early days, or once again, this is around 100 years ago that people were thinking about this, and they derived these theories which have these extra degrees of freedom that didn't discuss our world, but they derived these theories with very interesting properties. For example, they have this SU2 Yang-Mills theory. And just a little bit of storytelling. So it's actually kind of interesting why people didn't know about that they actually derived this. And actually Yang-Mills actually wrote down and had a paper and had this theory named after them. And this is really a reflection of fields, of the different fields. So in the early days, so particle physics was particle physics, quantum field theory was quantum field theory, GR was GR. So this is 2 separate, very distinct fields. People didn't really pay attention to what the other field is doing. So really in the early days, general relativity was describing something on big scale, and quantum field theory, particle physics was talking something on small scale. So the people who go to general relativity conference don't go to particle physics conference, and vice versa. So they didn't really talk to each other much. And that's what happened. That's why Yang-Mills wrote down this Lagrangian, and they had this Lagrangian named after them, even though in the gravity community, this was already derived around 100 years ago. Okay, this is a little bit, of course, nowadays, this is no longer true. Starting from around the 60s and the 70s, really the two fields start to merge together because of the emergence of the importance of quantum gravity and all of these various new frontiers in physics. So now the gravitational field and the particle field has merged together, and sometimes we call it high energy physics. And there's very different overlap. Okay, so now we have the Yang-Mills Lagrangian. So let's just see what was very special about Yang-Mills Lagrangian. So this will just take me 5 minutes, and then we'll take a 10 minutes break. Okay. So the Yang-Mills Lagrangian, why was it so famous? So because if you write this thing out, so let's just write this thing out. So remember, we know what the field strength looked like, right? So we've written the field strength here. Okay, actually, let me just copy and paste. So we already know that the field strength takes this form. So let's use that. So the field strength takes this form. Okay, actually there's a GC here. So this is the, sorry, this is, so of course there's two of these things here. So really there's this guy, and then of course there's the other guy. Let me put another I here. And then this is partial mu A mu upstairs. Let me call this, if this is C, let me call this whatever. D, let me call it D for a lack of imagination. So maybe let me call this D, E, F, D, A, mu, D, sorry, may do A mu E. And a new F. Okay, and of course this multiplies by GD. Okay, and of course we have the entire thing in trace here. Okay, so this is equal to that. And you can use that these are, or you can write the generators in an orthogonal form and properly normalize it. So we'll let the generators become orthogonal. So this is just delta DC. Okay. Therefore, this entire Lagrangian becomes minus partial mu A nu C minus FA B C A mu A nu B times, let me write the C where it's contracted, minus F D E C. Sorry, this nu should be upstairs. Okay, so we can expand this out. So once again, this Lagrangian has a quadratic term, quadratic in your A field. So let me just write this out. So you have this term and this term here. So I'm going to just schematically write this out. So you can have a derivative A here. So this is what we call the kinetic term. And in fact, this kinetic term has exactly the same form as what you get from your Maxwell theory. Okay. But because of the fact that you have these non-trivial FABCs, why is there this little thing here? Okay, because of the fact that you have this non-trivial FABC here. So now you're going to get something like FABC A, let me call it A, B, and then partial AC. And then plus two FABC terms with A. So these two terms are the new terms in your Lagrangian that you've never seen before in the Maxwell equation, in the Maxwell Lagrangian. So what these terms represent is that now, previously when you were having the Maxwell equation, the A and A is just propagating. It just has some kinetic term. There's no interaction between A. So this is, again, once we've emphasized many times that the Maxwell equation, electromagnetism, is a linear theory. right? The equation of motions for A is always linear, right? That's why light waves can pass through light waves without changing. But once the symmetry that you're talking about is non-abelian, you start to have nonlinear interactions. So now you can have interaction. If I draw graphs, you can have 3-point interactions, and you're going to have 4-point interactions. Okay, so this is really the new feature of Yang-Mills theory, is that when the local symmetry becomes non-abelian, the correction terms or the gauge field that you introduce will start to interact with itself. Okay, it has self-interaction. Okay. Okay, great. So this is a general non-abelian theory for non-abelian gauge field. So we basically set everything up ready now, and now we're going to focus on a particular choice of gauge group. So we're going to choose a particular set of gauge group. So we're going to consider so we're going to consider the local symmetry group to be the Poincare group. So once we focus the local symmetry group to be the Poincare group, then we get GR. Okay, so that's the punchline. Okay, so we're gonna see how GR gets derived. Okay, so let's take a break for 10 minutes here. So I guess it's 18. So well, let's just do 7 minutes, since I probably just do around probably just 30 minutes after this. So let's just take a quick 7 minutes. So let's come back at 25. Okay. So is there any questions? Okay, if not, let's just take a break. So I'll see you guys in 27:25. All right, see you guys. Okay, great. Now let's focus our symmetry group to a particular group, the Poincare group. Okay, so of course you might imagine that there should be something special. I mean, we can talk about Yang-Mills theory for arbitrary group, right? For arbitrary random group. So there must be something special about the group that gravity chooses. And indeed, there is something very special. And there's something special with the Poincare group. So for those of you who are not familiar with with this kind of nomenclature, so what is the Poincare group? So the Poincare group involves two sets of generators. One is that in principle, it corresponds to the group generated by translation. And the Lorentz rotation. Okay, so of course we can write. So if I use P mu and M mu nu as a representation as a representative for my group algebra, then this satisfies P nu is equal to 0, and for example M mu nu with P, let me call it rho, equals to eta rho mu P nu anti-symmetrized, and then I have M mu nu M rho sigma equals to eta mu rho M nu sigma minus eta nu rho M mu sigma minus eta mu sigma M nu rho, and then plus eta nu sigma M mu rho. Okay. Okay, so this is just how the generator works. So these are just the usual Lorentz generator, and P mu and P nu are the translation part. Now, how do we usually represent our generator? So for the translation part, of course, we usually represent our generator by translation, right? So that means that usually we represent our generator by minus I partial mu. Okay. As for the Lorentz generator, that depends on what kind of object you're acting on. If you're acting on a Lorentz vector, then you have mu nu, which is going to be like a vector form, right? Which is something that we have before. And sorry, this is -1. If it's acting on a spinner, a spin 1/2 representation, then your mu nu is going to be written as the anti-symmetrization of gamma mu gamma nu with 1/2, where gamma mu gamma nu satisfy what is known as the Clifford algebra. Okay. So these are, for example, the vector. So vector transform under this Lorentz generator, while spinners transfer under this generator, where this gamma mu is going to be 4×4. These are 4×4 matrices that satisfy this algebra. And this is also one of the important points that that motivated us discussing this is, of course, as I mentioned before, that when you're talking about spinners, we require, it's essentially defined through this equation, right? It's defined through gamma, where gamma forms the representation of your Lorentz group, and gamma is defined with this algebra, where this algebra on the right-hand side is just the usual flat metric. So in other words, these spinners are defined, so these spinners are defined when the space is flat. Okay, because you're defining this algebra. If this thing has the right-hand side to be some function, some g mu nu function, then this is no longer just matrices, isn't it? That you cannot use this to define things. So in order to define spinners, you really need to have something flat. Okay, and this will become important as we this will help us. This will become important point, which will allow us, which our formulation will allow us to define spinners in a consistent way. Okay, but before going there, now we see that there's a very important point, which is that we're going to make both of these symmetries. So we're going to make both of these symmetries into a local symmetry. Okay. However, one of these symmetry generators is the same thing as the derivative. And so we'll see what effect does this cause. So once again, we have that. So basically, we're saying that GR is basically a discussion of a local symmetry transformation, where G again is equal to exponential, let me call it lambda, where the lambda, or maybe let me just call it big G. So it's just some big G transformation, where now the G involves the generator of translation plus Lorentz transformation. So that means that my G involves, let me call this lambda mu partial mu, okay, plus, let me call this 1/2 lambda AB MAB. Okay, so this is just the gauge transformation parameter, for translation. So this is a function of x, and this is for Lorentz rotation. Okay. Now you notice that I have two different indices here. I have A, B here, and I have mu here. So from now on, we're going to, so this is related to the fact that we're going to think about our space as having some manifold. So at each point in my manifold, I can always, so I mean, one of the fundamental definitions of manifold is that at any given locally, and if a manifold is in dimension, then locally the manifold will look like Rn, right? It's locally, it's just flat. So that means that locally you can set up an orthogonal, for example, you can set up an orthogonal basis locally, And then the indices for this orthogonal basis is just going to be our AB indices. Okay, so these we will call, so importantly, from now on, these we will call flat indices. Okay, and these will be, so of course we know that that we can have coordinate charts here. So these will be x mu, x nu. So these will be our curve indices. Okay. Now, of course, this is translation, right? Because you guys know. So if I don't care about, if I forget about this for the moment, if I just take this, if I have g equals to exponential lambda mu partial mu acting on, if I have this, then g acting on a function f of x will give you will become f of x plus lambda, right? I mean, that's how this, that's why this is a generator. It generates a translation and excerpt in a particular direction. Okay, good. So, but it's basically the same thing. So once again, it's always the case when you're doing local transformation, you're writing a local transformation parameter multiplied by the generator of that transformation. Okay. So for example, so the different fields will transform different way. So for example, a scalar field will transform under this transformation as lambda mu partial mu acting on phi. Can someone tell me why I don't have any lambda AB transformation on my scalar field? I mean, I have my lambda mu transformation on my scalar field. Why don't I have lambda AB?
Because it's scalar.
Good, because it's a scalar, right? What is the definition of a scalar? The definition of a
Invariant.
scalar, exactly, it's invariant under Lorentz transformation, right? But it's not invariant under translation, right? Because a scalar field is a function of x. So under a shift of x, the scalar field will still transform, right? So once again, now you see again that it's impossible to write anything that is a function of x that does not transform on the local symmetry of gravity, because if the gravity is has a local symmetry of Poincare symmetry and Lorentz transformation, anything that is a function of x will transform under the translation, right? So anything that is a function of x will not be invariant under this transformation. So it's not gauge invariant. So this is one of the important things which we'll come back to in the end, which you guys have already heard me talk about before, which is that there's no local observables in gravity that is really well defined. Okay. Oops. Sorry, 1 second. Okay, good. Of course, similarly, if I have a vector field, so I'm going to use flat index to represent my vector field. Again, this is x. Of course, this will always be there because it's a local function of x. But then because it's a vector field, therefore it will transform. It will have an additional transformation where this lambda b rotates the vector. Okay. And similarly, if you have a spinor field, so I'm going to use this alpha index to represent this field being a spinor. Once again, it will have the same transformation. So anything that is a local field will all have this translation acting on it. But the way that it transforms under the Lorentz transformation depends on what representation it is. So for spin 1/2, it's going to transform under the alpha beta representation. So for those of you who've learned particle physics, you'll know what this representation means. For those who've not, you need to learn a little bit about spin 1/2 representations, which we can talk in private if you're interested to, or you can just look it up in any standard textbook. Okay. Okay, good. Now, so once again, we have our SOP, right? We already defined your generator. So that means that we can write down a covariant derivative. So so let's write down a covariant derivative in flat space. Now comes the tricky part. Well, first, let's just do the non-tricky part first. So remember that you're going to have the derivative, right? In principle, we're going to have a derivative in flat space. And if you're going to have the derivative in flat space, then we're going to have correction terms, right? We're going to have correction terms. And from the previous discussion, we see that the correction term should multiply by the generator, right, of the symmetry group that you're going to make local. So what generators do we have? Well, we have, of course, this Lorentz transformation. So that means that I can write A, and then let me just write BC and BC here. And since usually it's defined with 1/2, so I'm gonna write the CB. I'm gonna put a 1/2 here. But then I also need, because I'm also making this this translation in X in my coordinate system. So that means I also need another guy, which is, let me just call this A, my correction term here, which is A. And I'm going to need that this A carries this index A, mu, and then partial mu. Okay. Right? This is our standard SOP. Once you have some symmetry group that you're trying to make it into a local symmetry, what you do is you identify the generators of the group, and then you write down your covariant derivative, where the correction terms to your covariant derivative has to be proportional to the generators. Since I've already identified the generators being translation and Lorentz transformation, therefore I have a gauge field associated with my Lorentz transformation, and I also have a gauge field associated with my translation. Okay. So does this equation look weird? Do you guys feel this is weird? Is there something weird about this thing? Anybody?
There are two derivative terms.
Exactly. These terms looks almost the same. Right? These terms look almost the same. So, I mean, they're just derivative. So there's no sense in actually defining them as separate term. So actually what we do is we just write, so we just erase this, and we erase this with the idea that I know that my AA mu, when I do, in principle, my AA mu should contain, and generically, should contain a delta A mu plus an extra term, let me call it A tilde A mu. So that the delta A mu term will reproduce the partial A that I begin with, and then this will be my correction term. In fact, this is indeed how we write this. So I'm going to write this. So this is the notion of Vielbein. So the Vielbein, we write it like this. And then this other A here, I'm going to call it omega A BC. Okay. So the omega ABC here is what usually called the spin connection. Okay, the spin connection is the gauge field for local Lorentz transformation. And similarly, this we call the Vielbein. It's of course a German word, which is, I remember the meaning is like stakes, because this literally is the meaning. It has the notion that at any point here, you can set up your coordinate chart here, you can set up different coordinate systems at different points on your manifold. And each coordinate system will will of course carry two indices, and it's of course a function of x, because where your axis set will depend on where on the manifold you actually are. And since this is Vielbein, of course, naturally the Vielbein locally and very small locally, the Vielbein naturally should have an expansion that looks like delta A mu, which is, that means that the Vielbein is exactly local, exactly oriented with whatever axis you have, plus the correction terms. Okay, so that actually makes sense. Okay. Okay. So that's GR. So GR is basically going from so it's basically starting with this covariant derivative. And so you see that the only reason that GR was special in this context is because the symmetry group that you choose to make it local actually includes translation, which includes this very interesting Vielbein structure here. Okay, so that's really the special thing that sets GR apart in terms of local transformation. Okay. So once we have this transformation, once we have this, we can immediately derive how each of these fields should transform, right? Because remember, once we have the, sorry, not once we have the transformation, but once we have the covariant derivatives, we know that the covariant derivative again, so now this should be so familiar with you guys. So the covariant derivative transform as G derivative G inverse, right? So in our case, it's going to be equal to exponential G delta exponential inverse G. Okay, so this is the homework that I want you guys to do. So the homework is to use this definition here. So use this definition. So remember my delta, so let's use delta A. Okay, remember my delta is now written as exponential A mu partial mu sorry, I forgot it was plus or minus plus 1/2 omega A B C M C B. Right, we start with this. And you can use that the generator. So for example, if once again, if MAB commutator with 8C, for example, this is just a vector. So this commutator is just eta AC EB, and then minus eta BC EA. And similarly with the thing that I wrote down before, MAB MCD is going to be equal to eta AC MBD plus the 4 terms that are written down, which are related to this term by the fact that these A, B, and CD are antisymmetric. So you can work out the algebra yourself. So you can take this. So we did this already 2 times already. So you can try to work things through. So you take delta A in this form, and then you plug it into the left-hand side as well as the right-hand side. And then once again, what do? You can then deduce how does the Vielbein and the spin connection transform under the gauge symmetry, right? So in doing this, you should derive, so I want you to work this out, you should derive that the variation of your Vielbein under the local Poincare symmetry takes this form. And I'll comment on this shortly. Just 1 second, let me just write this out. And then we'll study this, we'll make some comments on these results right after. Okay. So this is how the Vierbein and the spin connection transform. So let's make a few observations. So this is the homework that you're supposed to derive. You're supposed to derive that using the fact that once we define the covariant derivative, this automatically tells you how the gauge fields in your covariant derivative should transform. Okay, and they're derived by the fact that requiring that the covariant derivative should transform covariantly, right? And so you see that this is how they look. And so let's take a little bit a detailed look. So notice that here the Vierbein transform as derivative acting on the parameter associated with the translation. But there's no derivative acting on lambda AB, which is the parameter for the Lorentz transformation. Similarly, for the spin connection, there is a derivative acting on the parameter for the local Lorentz transformation, but there's no derivative acting on the parameter for the local translation. And the reason is simple. It's just that as we derived before and in our previous discussion, we've seen that, importantly, that anytime we have a gauge field, the transformation of the gauge field will at least be proportional to the derivative of the transformation parameter in which this gauge field is associated. Okay, so the transformation of the gauge field will be related to the derivative, will contain a term that is the derivative of the parameter in which your gauge field is associated with. So in our case, sorry, what am I doing? All right, never mind. This is still faster. So in our case, indeed, we see that, remember that the Vierbein is associated with local translation, right? Because it's this multiplying by the local translation generator. And therefore, the variation of the Vierbein contains a term that is derivative of the parameter that is associated with local translation. And similarly, the spin connection is the gauge field for local Lorentz. And therefore, the transformation of the spin connection involves a term that is the derivative of the local Lorentz parameter. Okay, but otherwise, everything is as they should be. I mean, and furthermore, you see that this transformation here involves, you see that the way that the spin connection transform involves something that is derivative of lambda plus omega lambda, something like a commutator, which is exactly the transformation that we've derived before in general, for general group theory, for general groups. Okay. Okay, so since once again, this is SOP, we derived that once we have the local symmetry, we write down what the covariant derivatives are. From the covariant derivatives, we can derive how the gauge field should transform under the gauge transformation. And then we just write down the field strength. So once again, we write down the field strength, the commutator of delta A, delta B. Now, there's actually on the right-hand side, so previously on the right-hand side, I would just write down the field strength, multiply. So remember previously we had the field strength multiplied by the generator. But actually, so basically the only requirement is really that because on the left-hand side, these are each covariant objects. So these are covariant objects. So on the right-hand side, you're supposed to write covariant stuff. So one of the covariant stuff is, of course, the covariant derivative. So really, if you really want to write things in full generality, the most possible general thing that you can write on the right-hand side, then this would be T A B C delta C plus, let me call this 1/2, and then R A B C D M D C. Okay, so here, this is the usual thing where we have the field strength that usually we write it MAB, but because my generator is now DC, So now I basically write MDC multiplied by DC, and then I call this thing RABCD. Okay. And there's of course a term because one of the generators is derivative, so that actually implies that you're supposed to write covariant derivative here, and therefore you're going to have this term. So really, the fact that the reason that you might have this term here is related to the fact that one of the generators or the symmetry group that we're talking about is translation. Okay. So as those of you some of you probably already guessed, this is precisely the Riemann tensor. Okay, so from this point of view, the Riemann tensor is again nothing more than just the commutator of your covariant derivative, in which your symmetry group is local Poincare symmetry. Okay, this is called the torsion. And for consistency later on, we'll see how to set this torsion to 0. So we'll basically talk about the torsion-free formulation. Okay, but now you're already gradually seeing how GR is already starting to appear in this kind of construction. So once you identify the local symmetry, you define the covariant derivative, you define the gauge field. From the covariant derivative, you derive the field strength. From the field strength, you build a Lagrangian. And basically, that's the end of the story in a nutshell. Okay, so we'll stop here. I think this is probably enough for a day. So we'll stop here. And so this will be the homework for this week, which is to derive the transformations. And next week, we'll pick up from this equation here where we define the Riemann tensor and the torsion field, and then we'll go forwards. And of course, as you might imagine, so there just to give you like a brief preview. So the relationship between the usual notion of metric and the Vielbein is that the metric is written as basically just eta AB, the flat metric multiplied by the Vielbein. So you can say that the usual curve space metric is just mapped from the flat space through this Vielbein to get the curve space. Okay, and of course the other thing is that we have this extra spin connection here. So you might worry that the spin connection, we have too many degrees of freedom because in GR we only talk about G. So why am I having extra things here? Because and you'll see in next week that there's going to be certain conditions that will allow us to set the spin connection to become completely determined by the Vielbein. Okay, once you know the Vielbein, you know the spin connection. So that means the fundamental degrees of freedom are associated with Vielbeins. Okay, and this will be our focus next week. And from this, we'll again derive the Einstein-Hilbert action as the most natural thing you can write down. Okay, so that's it for today. Is there any questions?
老师，我可以问一下那个 covariant derivative 的 commutator 吗？
嘿，
就是
这个是
他之前计算的时候，
这个
就是对，在前面一点的
都在
它的 commutator，
你说在 general discussion 的地方是？
对对对，
So sorry. So here,
对这个，
yeah. So
我想问一下，为什么没有 a mu partial mu 减掉 a mu partial mu 这一项？
a mu partial a mu. Sorry， 再讲一遍。
a mu partial mu 减掉 a mu partial mu。
你说 partial 在 a 的后面。
对。
Oh, yeah. That's okay. So in the computer, so the question is that. Sorry, can you turn off your mic when you're not speaking? Sorry. Yeah. So the question is that why don't I have a partial stuff here? And the reason is because that okay. So so this has actually. So this is. Let me just do. What? Oh, this is the thing. Yeah. Okay. Sorry. Right. So let's just say we write down partial mu plus a mu let's just work this out. Partial mu plus a nu. So there's going to be 4 terms, right? There's going to be equal to partial mu minus partial mu plus so for example, you're going to have this partial mu a nu plus this term partial a plus a mu partial nu, and then the anti-symmetric one. Right. So the question is that why don't we have these terms? Now, importantly, because this is acting, so when we're having covariant derivative, we're thinking that there's actually other stuff that's going to happen here, that this will be multiplying. So when we're acting the partial mu here, the partial mu will act on a nu. So this will become, this term will become partial mu a nu with the parentheses, which means that this partial mu is fixed acting on this guy, plus additional term, which is a mu partial mu. Okay, so this term will become 2 different terms. And as you see, that because it has 2 different terms, so this term will cancel this term here. And similarly for this guy, you're going to have partial nu a mu, and then minus a nu partial nu. And this term will cancel with this guy. Okay?
好，谢谢教授。
Okay. Is there any other question? Okay, I guess we had enough. So that's it for today, and I'll send you guys a more detailed. So I'll write everything a little bit more clearly, the detailed version of this homework, and I'll send it to you probably in a couple of hours. Okay, thanks everyone. I'll see you guys next week. Bye.
Bye.
拜拜。